the rate detection, to remind you, the idea is to look for the scattering of dark matter on some target material and detect the energy that is left over by the interaction. So we have some material here, dark matter goes through, interacts with it, and leaves some influence. We can discuss what kind of influence can leave at a later stage, but the idea that we are trying to do, that people are trying to do right now, is to kind of figure out what are the, how do we calculate, what is the rate, what do we expect from the rate of interaction between dark matter and whatever our material is. And we saw that it depends on three types of information. So we needed to know the astrophysics. We needed to know the high-energy physics theory. And of course, we need to know the details of the detector. And the rate is going to depend on each one of these parameters. And what we're trying to do is to walk through one by one and figure out what is the information, what do we assume, and what is the rate. Okay? Questions? All right. So I think we finished by discussing, so we're now talking about astrophysics, and if I remember correctly, we start with the discussion of the density distribution. Okay, so we said that there are these n-body simulations that give us two things. They give us the density and they give us the velocity. So we saw what is being used here. Let me now tell you about the velocity distribution. So most times when you see bounds on from the rate detection, the assumption is that the velocity distribution is just Maxwell-Boltzmann. Okay, so we have the Maxwell-Boltzmann distribution, which is the following. It depends on two parameters. It depends on the average velocity, which we believe is in the galactic center. Is in our galaxy, and on the escape velocity away from the sun, away from the galaxy. So this is the distribution times some theta function of v minus v escape. Okay, so it's just a Maxwell-Boltzmann distribution where LE is V0 squared over pi, because we have times, we just the normalization f function of z is square root of pi into the number v squared, where z is v escape over v naught. Okay, so just a normalization of this distribution function. And v naught, the average velocity, is typically taken to be anywhere between 220 kilometers per second and 270 kilometers per second. And v escape is anywhere between, say, 450 kilometers per second to 650. Okay. So this is an assumption we're taking these ansatz, and as we discussed last time, you have to remember that you don't really know what the real answer is. There are large uncertainties. Now, this F critical is not the thing we are interested in. This is the velocity distribution in the galactic frame, namely the center of the galaxy, moving to the center of the galaxy. We are interested in the velocity distribution around Earth. Okay? So let me remind you, we have the sun that moves in some velocity, which is this v naught, and we have the Earth rotating around it with another velocity, which is 30 something. The Earth, which is roughly 30 kilometers per second, and so the real velocity, the real distribution that we're interested in is F Maxwell-Boltzmann, of some V observed plus V. And again, there's this V0 in this case. Okay. So this rotation is very important. As we mentioned, what we're going to see is this wind of dark matter particles because of this motion. But because we are rotating against around the sun, this wind will change, okay, as a function of time. So we're expecting to see annual modulation of this wind, of this velocity distribution. So this will be a function of time here. And we expect to see annual modulation as we rotate around the sun. And we'll talk about it later. There are experiments that do exactly that. They search for this annual modulation, the change in the rates, because the dark matter wind changes, the velocity of the dark matter wind in our frame changes throughout the year. Okay, is this clear? Okay. So what is this V observed T? The observed velocity is just roughly given by V sun, the velocity of the sun, plus the velocity, some small parameter times the velocity of Earth times cosine of omega T minus Tc. Okay, so as we said before, this is roughly 30 kilometers per second, and V sun is roughly 220 kilometers per second. And this Tc is the time where the velocity is maximized. And this is roughly 0.45 when we are talking about omega, which is 2 pi over year. So this is units of year. So 0.45, 415 is June 1st. So this is crucial. If we see modulation, we should not just look for a modulation, we look for a modulation where we think that the peak should occur on June 1st. Okay? So we look for this modulation, and this modulation should have a phase consistent with the picture that we have for the rotation around the Earth and us moving against the halo, the dark matter halo. So speed is 0.5 roughly. This is 0.5. Okay? Question? So that's just technicalities. That's the velocity distribution that people usually take, but as we said, there's a relation, there's a relation between the velocity distribution that we have and the profile that we have, that one gets. It's not these are not independent. And hence, for most profiles that I showed you last time, this distribution is just inconsistent. And once you take a different answer, which is more consistent with the profiles that everybody simulations find, and the one answer that sometimes people use is the following. It's some profile that is proportional to e to the bsk when v squared over v, k v not squared minus 1 to the power of k. Okay? And k is often taken to be 1.5 and 3.5. So if you drew this, you would see that there are larger uncertainties. What we're going to find now is we're going to derive the rate as a function of the velocity. In particular, as a function of the minimal velocity that the dark matter has to have in order to leave an observable imprint. And so all these distributions behave somewhat differently in the tail. So I mentioned it last time. And these uncertainties on the tail of the distribution impose an uncertainty on the rates that we expect from dark matter. So this is something to remember. And of course, this is just one solution. We could have streams of dark matter move through. We don't know whether we are maybe in some, there's some stream of dark matter that goes through our galaxy, or a galaxy is inside one of these streams. And so there are large uncertainties that are related to this velocity distribution of dark matter. Okay? All right. So that's what I have to say about the velocity distributions. Let me make one comment about how the local density that we use in the dark matter. So it's pretty hard to measure the local density. Certainly not doable with dead body simulations. We don't take into account variables. We are asking about a specific location. And so we really have to measure somehow around us how much dark matter we believe there is. Now, very, very roughly, we have the following. If we want to see the dependence on the velocity of the rotation curves around us, then the Newton's equation that dictates it is just that. Right, it's just the mass gn over r squared, which is the acceleration. And, okay, that I can write as g over r squared times 4 pi times the r prime squared. I'm assuming that it's rotationally, that it's spherically symmetric. That is the square of r. And therefore, and therefore, if we take the derivative of this equation, we find the rho of r equals 1 over r squared times d to the r of v squared of r times r divided by, I guess, 4 pi g. Right? Yes. Okay, so if we measure the change in distance of the velocity rotation curve as we move up in the galactic plane, we can derive the density Okay, so this is in principle doable. It's much harder than it sounds. What we really need to do is to be able to differentiate between the potential of that causes the rotation due to baryons and due to dark matter. Luckily, the dependence on, so we have a galactic plane, so our galaxy has some small galactic plane, and the halo is of course much larger. And as we move up, where we're sitting here, as we move up in the galactic plane, the dependence on the density of matter and the density of dark matter is different, because as we move up in the galactic plane, this is constant, and we are still feeling more and more dark matter as we move up. So there's different dependence, R dependence, due to the two components, and therefore we can differentiate them. And what people really do, they don't really use this formula, but they make some assumptions and they make a fit, and they derive the local density using these measurements. And we said it already, it's anywhere between 0.3 to 0.4 GeV per centimeter cube. Okay, so that's the local density that we'll be using. Of course, just a comment, if this is wrong, so we believe this is the number, but if this is wrong, the number density, sorry, the rate of interaction is proportional, it's going to be proportional to this. So, if this is wrong by a factor of 10, we'll be expecting our sensitivity to cross-sections will be reduced by a factor of 10, or enhanced by a factor of 10, depending on which way it goes. Okay? So this is just the overall proportionality constant in front of our rate, as we'll see in a moment, and therefore the uncertainty translates directly to the uncertainty on the cross-sections. Okay. Good. So now we can talk about scattering rates. So we're done with the astrophysics. In a moment we'll see that all of this astrophysics enters into a single function in our rate, and this single function takes into account all of the uncertainties, all of the information that we get from astrophysics. So we'll be able to divide the rate into some astrophysics part times some hydrogen part. Okay? In the lab frame, this is now what we are interested in calculating. We have some nucleon or some atom, A, that interact with dark matter and scatters off. The velocity of dark matter is roughly 10 to the minus 3, right? V naught was 220 kilometers per second. That's roughly 10 to the minus 3 times the speed of light, the velocity of light. And therefore, this whole exercise is trivial, literally non-relativistic quantum mechanics. So we can do the kinematics. You can do the kinematics. And what you would find, right, just equating the conservation of momentum and energy. And, oh, very important, we are talking about elastic scattering. I will make a comment later about this assumption that the scattering is elastic, that what we are looking for is an elastic scattering. You will see that this makes the whole the process, the searching for elastic scattering is extremely inefficient when we go to low masses. Okay, so searching for WIMPs of order the 100 GeV, of order the mass of the nucleon of the atom, is perfectly fine with elastic scattering. If we want to go lower, if we want to search for dark matter which is lighter than, say, the GeV scale, look, doing elastic scattering is extremely inefficient. So I'll show you that in a bit. But for now, we're just discussing elastic scattering. Dark matter interacts with an atom and scatters off. All right. So there's the momentum transfer. The amount of momentum that is being transferred by the dark matter, this is just n chi V in minus V or V out minus V in. And you can work it out. I'll write the exercise in a second. But you can work it out and you see that the momentum transfer squared is just that. Where cosine theta star, so this is theta star, star denotes the center of mass. Okay, so in the center of mass frame, this is the angle between the incoming and outgoing of the dark matter. And mu here is just the reduced mass. So again, this is the first year exercise, so it's just n chi MA of line. Okay. So, what is the recoil energy? The recoil energy is just how much energy is left onto the target. Well, that's just the energy of half and pi V out squared and V in squared, which is the same as Q squared over 2MA. Okay? This is just the energy, the recoil energy. And then we can write, well, it's just that, so it's mu squared V in squared over Mn times 1 minus cosine theta squared star. Okay? And I'm going to write it as the following. It's the energy, the incoming energy of the dark matter times 4 mu squared over n chi plus Na times 1 minus cosine star over 2. So there's nothing especially what I'm writing. This is just the energy of the incoming dark matter particle. This is a variable, we call it R. It is a variable anywhere between 0 and 1. And this is the angle, the suppression due to the angle. Okay, again, anywhere between 0 and 1. So of course, the recoil energy is smaller than the incoming energy, the energy of the incoming dark matter. And it is maximized, here recoil is maximized when it's R equals 1 when n chi equals Na. Okay, so again, mu is then just 1/2, so this is just pi. Is that correct?
It should be squared in denominator probably.
Yeah. I'm confused myself.
The dimensions are.
Sorry?
The dimension of mass is wrong.
There's a mu squared.
Yeah, I'm missing a factor of 2 somewhere.
Wait. I think it's dimensional. Like there's mu squared and there's mass squared over mass multiplying the.
Oh, I'm sorry, thank you. I guess this is a square, yeah. No, it's not square, because not square here. That's what it is. I'm sorry. That's it. Yeah, well, simple manipulation. Okay. So that's good. Now we can ask the following question. For a given recoil energy, for a given momentum transfer by the dark matter, what is the minimal velocity that we need for this to occur? Right? So you see that, of course, we have this angle that we depend on. So you can show that V min for a given Q we recall V min is just Q over 2 mu, which can be written as Nn ER over 2 1 over mu. Okay? So there's a minimal velocity. If we want to see an imprint, why is this important? Because we are looking at the spectrum. Eventually, what the ray detection experiments will be doing for us is just measure the number of events as a function of the E recoil. So they measure this E recoil in some way, and we're going to see some spectrum. We'll understand the spectrum. But they will be measuring that, and for a given event that they see here, then we will need to know what is the minimal velocity such that dark matter can imprint with such a recoil energy. Okay? So there's a minimal velocity that is involved. So here's a simple exercise. So again, in my notebook it's 7, I have no idea. So first derive the kinematics for the elastic case. Just the thing we worked out, nothing special. Then, tell me how does the kinematics change if the scattering is inelastic, but not inelastic in the sense that I'll mention later, but is inelastic if scattering is inelastic by which I mean that the scattering now will happen from some dark matter to some excited dark matter. So we have the atom coming in, the dark matter coming in, and what's coming out is some excited state. Namely, there is a delta, which is n chi star minus n chi, or maybe that is star, not whatever. Well, it doesn't matter. So if we have some mass differences, imagine that, we'll talk about it later, imagine that dark matter scatters through the Z boson, for instance, and this dark matter doesn't couple diagonally to the Z boson, namely, the two eigenstates that couple to the Z are such that upon this interaction, we move from some state chi to some state chi star, okay, with some mass difference. Imagine that this mass difference is relatively small. Then the kinematics is very different. V minimum is very different, so actually let me tell you, just tell you the final answer. find that in this case V minimum is just 1/2 mn r times mn r over mu plus delta. This is a crucial difference compared to the case where delta is 0, namely if this term dominates over this, then now the minimal velocity drops for heavier targets, opposite to what we see there. The spectrum is actually different, and there have been a lot of games within elastic dark matter in the past, I don't know, 10 years or so, maybe even less, because they were trying to evaluate the tension between gamma. We talk about an experiment that sees an anomaly and other experiments which have null results. And the idea is that once you have this strange dependence on the mass of the target, you can see an effect in heavy targets, but not see an effect in light targets and so on. So there's going to be there's a whole game that people have played with this type of dark matter candidates, which interact inelastically with the nucleus. Okay? And so I encourage you to work this out. It's simple. Again, if you suggest, there's nothing more than just non-relativistic kinematics. Questions? Okay. So what is the scattering rate? So I promised before, I really mean it. What is the scattering? So by the way, when I mentioned gamma, how many of you have heard about this experiment and the results? Alright, so we are interested in the following. We are interested in calculating the R, the ER, namely the differential rate of events for a given recoil energy, with a function of the recoil energy. Pretty simple. It's n sigma v, the differential cross section, times v, times the small number of the dark matter elements at a given v. So for a given velocity, which will give us a given recoil energy, we have some small number of differential number of dark matter particles with a distribution which with velocity anywhere between v and say delta v. Okay, so that's the idea. It's just n sigma v only in the differential form. And we know what this is. This is nothing but first all the particles which have velocity greater than the minimum velocity and the number density is the following, is just the local energy density divided by the mass, that's the number density, times the distribution of V, d3V. Okay, so that's just the n. It's the total number of the density of dark matter times the number of particles that we have with some specific velocity. Is this clear? Good. So what does that look like? Well, this is true for a single target particle. So that's the rate of dark matter interacting with a single target particle. If you want to have a target material with, say, Avogadro number of targets, then we have to multiply by NT, overall number of target material, target particles. So all in all, we have the following. Okay. So NT is just 10 cubed the number, the Avogadro number over the atomic number of the material per kilogram. Okay, so how many particles do we have in the kilogram of material with atomic number 8? That's just the answer. This is the Avogadro number. Okay. What is the unit of R? Sorry, second?
Number of lengths per second.
Almost per kilogram. Per kilogram per second. So kilogram days. So you will often open the papers with the rank detection experiment, with the rank detection results, and what you see is that they have collected, say, 100 kilogram days of data. And they find, unfortunately, no dark matter. So that's the unit of the number of events that they see. Right? So you need to multiply whatever you calculate by 100. Now, because the recoil energy is proportional to V squared, then that means that the sigma DER is proportional to V squared. And therefore, this integral is typically of the form, we have an interesting integral which is d3v, there's 1v here and 1 over v squared here, so it's d3v over v times f of v. This is often denoted eta, and what is it a function of? Right, so it's just the mean velocity. So this is the function that would encode the full information, all of the astrophysics in that we've assumed, and if we just take different distributions or different dependence, velocity dependence due to this sigma, we would have to change this eta to the corresponding eta that we care about, but this will hold all of the information. It depends on E recoil and on V minimum. Let's just see what it looks like. Okay, so, well, I should just say that this is just the velocity average of 1 over v times the theta function, v minus v. Is this readable? This is nothing more, this is some distribution of velocities, and what we are measuring is 1 over v times theta. That's all. Okay, so let's just try to roughly see what it looks like. Well, for simplicity, let's just take f of v, equals Ignore the escape velocity, ignore the rotation of the Earth and the Sun, so just work in the galactic frame, and let's just compute what is this integral. So what we have is the Maxwell-Boltzmann. So this is for simplicity. Okay, and therefore eta of V mean equals what? Equals the integral of this dv over v times 1 over pi v naught squared to the 3 half v to the minus v squared over v naught squared, which gives you a 4 pi over pi v naught squared to the 3 halves integral of dv and v e to the minus v squared over v naught squared, which is the same as putting a 2 here and calling it dv naught. And this is for v mean to infinity. There's no escape velocity. This is just infinity, doesn't matter. And okay, so this is just square root of pi e to the minus v mean squared over v naught squared, which I can write down as e as square root of pi square root of pi times e to the minus e recoil over the average e recoil. This we should leave somewhere. Write it again. Okay, so this just follows from the fact that V mean equals Q over 2, Q squared over 2 mn, which is, I remind you, mn er over 2 mu squared. Right, so I just plug in the relation between V mean and dr, and what I call my average ER is just ER and V equals V naught. Okay? So my eta, my astrophysics, what it does is give me some function, right? The function of ER. It will give me a foreign function that will affect my spectrum. So elastic scattering, because of this eta, we expect this to be a foreign function. It will be one factor out of 2 exponential foreign factors that will affect my spectrum. So let me write down the rate again. Are there any questions? Speed up a little bit. So again, the rate, write it down for the dexterity. You just nt and integral t v p times f of v times nt rho sum over n times sigma dr. Right? So this is the high energy. This, together with the velocity dependence here, is the astro. This integral, well, this is the astro information, and that's just this is just the target. So the experiment. Okay. So just to get a feeling of what we expect this number to be, let's just define R naught to be nt times rho sum over n, right? times some sigma naught times v naught. Okay, so I'm taking the usual, some average velocity and some standard cross section. So we can plug it in. This is, as we said, this is 10 cubed Na over A kilogram to the minus 1. That's the number of targets. Let's call that point, say, 3 GeV per centimeter cubed divided by, say, 100 GeV of dark matter. Let's take a cross section, sigma naught of picogram. And V naught is 220 kilometers per second. And when you plug it in, you get that this is roughly 4.5 over A events per kilogram per day. So that's not a lot. We're talking about an integrated rate of roughly 4 events per day, or usually A is much larger, usually A is more than 100. So we're talking about, say, 10th of an event per day per kilogram material we put down on the ground. Okay? So that's the rough numbers we have to keep in mind. Question? So what is the overall rate?
So there is one question. We have integrated distribution function, but is it possible that cross-section also depends on velocity of matter particles?
Absolutely. So that's what I said. Yeah, absolutely. So in principle, this is we're now estimating the simplest case. Simplest case where this is just a variable v12 that shows up because of the recoil energy, but nothing else. But in principle, this would depend, we'll talk about it, it would depend on velocity, it would depend on momentum. It could be velocity suppressed, it could be big suppression, it could be momentum suppressed, and then the rate would be even smaller and the sensitivity goes down. Okay? But we don't know what it is, of course. So you need to keep it open mind. We'll talk about the effective theory in a moment, how we parameterize all these possible. So we're going to talk about the high energy part of this rate in a second. Right now we're just trying to get a general picture. Okay, so what is the R? The ER? Well, it's, so we wrote it down there, up there. So now I'm going to write it the following. It is just R naught over the average recoil energy, which is 2 mu squared V naught squared over Mn times eta of V min times V naught. Okay? So we plug in all the numbers, and what you find is that this is roughly R naught over the average E recoil times E to the minus E recoil over the average E recoil. Okay? So we have this exponential form, and we have the average number of events that we expect. Okay. So now a short remark that I already mentioned before. So we didn't look at the numbers, but we saw that the momentum transfer, so remark. We saw that the momentum transfer is roughly 2 uv, which if that matter is light, okay, so let's just see what it is. V, remember, is roughly 10 to the minus 3. So for, say, 100 GeV, dark matter, this is roughly 100 MeV. Very roughly 100 MeV of M psi over 100 GeV. That's roughly the momentum transfer. The recoil energy is Q squared over 2Mn, which is roughly, say, 10 to 100 kV. Okay? So the energies in our experiment need to be able to measure are of order tens of kV. for 100 G viewing, and the momentum transfer is roughly 100 MeV. This will be important when we talk about coherence in a second. But for now, let me just. So you should know that most experiments, the threshold, the state-of-the-art experiment, the threshold is roughly anywhere between, say, 1 to 10 keV, depending on how the experiment and what are its capabilities. Usually, the ones that are able to get rid of background matter have a slightly higher recoil threshold of order 5 keV or so. So that's what we are fighting against. But what happens if you want to go down in mass? So you remember that when we talked about the mechanisms of production, we saw that the WIMP is extremely motivated because of the fine-tuning problem, because of theory. But the interesting part is that it's heavy. Okay, so we are extremely happy because our technologies allow us to look at heavy particles because the recoil energy that they give is sufficiently high. Okay, but what happens? Can we probe anything lighter than that? So what about light dark matter? So the common law is that it's extremely hard. Well, that's definitely true, but it's impossible. And the reason that people were saying that it's impossible is exactly because they look at these scatterings that we've discussed right now. So the recoil energy goes like, so let me write the recoil energy again, goes like roughly M dark matter. Remember the Q is proportional to the reduced mass, but the reduced mass is the lighter of the two. So if we talk about light dark matter, it's just the mass of the dark matter. So this is roughly M chi V squared over M. Okay? So it is something like that. If this is say EV, and this is KV, and this is the mass, which is MEV, and EV, and say T. Okay, so if I draw roughly the dependence of the recoil energy, U recoil, as a function of the mass of the dark matter, then it drops like M squared as we go down to lower energy, because this is roughly our threshold, that's roughly the limit. We are limited roughly at the 1 GeV. We cannot go down below 1 GeV. But, so that's the energy that the dark matter leaves. But how much energy does it have? Well, that's easy, right? The energy of the dark matter is just half M chi V squared. It only depends on M chi, and it is much larger. In fact, it goes something like that. So the energy that the dark matter has is much, much larger than the energy that it leaves in our detector. So in principle, if we were thinking about something else, we could go down to much lower masses as long as we are not looking at these elastic scattering. Okay. So looking for light dark matter is extremely inefficient when we want to do when we look at elastic scattering. So what can we do? Any ideas? So again, I should motivate you. The bottom line is that we really don't want to be in the situation that we are only probing the winds, because we, as we will talk soon, we see that first we don't see them, and soon we run out of options. Namely, we reach the limits that we can search for these winds. On the other hand, the motivation, the fine-tuning problem may go away if we don't see anything in the LMC. So we want to break through, we want to go and search for different types of dark matter, not just the WIMP, not just the freeze-out particles that we, thermal freeze-out particles that we discussed. It's just one single production, there are many other production mechanisms. So how do we do that? Well, we just don't look for elastic scatterings, right? Elastic scatterings are inefficient, just look for inelastic scattering. So there are all kinds of options. interact with the electron. Right? So you have the atom and the electron, and if dark matter interacts and kicks an electron and releases it, there's an inelastic scattering, which requires much less energy. It is much more efficient at collecting the energy from the dark matter, and it's possible to search for much lighter dark matter. So this is a technology which is starting to be used with several experiments. So that's one thing. Another one is to excite the electron excitation. You kick the electron and then so you, well, okay, so I guess the picture is we have whatever target we have interacting with dark matter and producing some excited states. For instance, by exciting the electron. The de-excitation it could be detected in principle. So this is another way. Third way is just breaking bonds altogether. For instance, molecular dissociations have a threshold of say a few eV, and again, once you look for an inelastic type of scattering, you can search for the imprints, and you can collect the energy much more efficiently. So this is a cyber map on how we make progress beyond the wings with direct detection, and all of this stuff is work in progress, and I encourage you all to think about it because I think it may well be where we are heading in the not so far future, okay, with direct detection. Okay, so where were we? Yeah, so the cross section. So we have, so we have this scattering rate, but now we want to know what is this cross section, the sigma, the R. How do we work out this cross section? What are the possibilities? And how do we parameterize? Then we write an effective theory that encodes all of the possible dark matter candidates and interactions of it with us. Okay, so how do we do that? So the recall energy is anywhere between 1 to say 100 keV, while the nuclear binding energies are much larger, of order 1 to say 10 MeV, and therefore, at least in order, we can just ignore the interaction. We can think about an effective theory where we interact with the whole nucleus. We don't need to think about the interaction with different nucleons inside our nucleus. So as long, or say it differently, as long as the Broglie wavelength of my dark matter that goes through my nucleus is much larger than the size of the nucleus, I have coherent effect. I see the whole nucleus together, and I don't need to think about the various interactions with different nucleons inside the nucleus. So there's a coherent effect that becomes very important, and we'll discuss it in a moment. But for now, let's just ask, what are the possible potentials that dark matter can fill, and what do they correspond to? Okay, is this clear, or is this confusing? Well, actually, let's make one more step and then we'll figure it out. So we want some effective, V effective, that depends on some parameters that will give us all of the information about how dark matter interacts with us. Luckily, it's pretty easy, and the reason it's easy, at least in order it is, and the reason it's easy is because we are, again, dealing with non-relativistic quantum mechanics. So this V can depend on only a few parameters. Any idea what they are? What can this potential, effective potential of the interaction between dark matter and our nucleus? Okay, not nucleon, nucleus. What do they depend on? Well, it's true that, that's right. There's going to be some constants here that are correspond to the coupling, but are.
Charge.
So we have a vector. So this is composed of vectors. One vector is just R, right? What other vectors do we have in the theory? Non-relativistic, one particle coming in. The potential of the dark matter feels as a function of matter. The velocity and spins. So it's the spin of the dark matter and of the spin of the nucleon. Okay. At least in order, this is all we need to do is to construct all of the possible effective potential we have as a function of this, and we're going to get and we'll be able to extract what is the form of the sigma dE given the specific potential, so that we can enumerate it. We won't do this exercise fully at all, it's not even close. But let me just give you some examples and comments. So, first of all, if the effective potential depends on the spin of the nucleon, we call this a spin-dependent potential, a spin-dependent cross-section. It will lead to a cross-section that depends on the spin of the nucleon. Okay. Conversely, if V effective does not depend on Sn, this is what we call spin independence. Okay? So in most papers that you'll open, you'll find that they constrain the interaction of dark matter due to some experiment, which has either spin independent or spin dependent interaction. This is highly suppressed compared to that. At least one reason we'll see in a moment, the coherence effect. Here we interact with the whole nucleus and we just know about its spin, and here we got many nucleons and we just sum because of the coherent effect, we just sum over all the nucleons, so there will be a huge enhancement for the cross section in this case. So we'll discuss that for now, well in a moment, but just know that there are two types of interaction, spin dependent and spin independent. You can actually prove it rather rigorously. So now we need the matrix element, and the matrix element for the scattering is just in the Born approximation. We are working in the semi-classical approximation. This is just this 3R e minus R to R and minus sign times the effective. Okay, so this is nothing more right than the wave function. You come in an ongoing wave function of the dark matter, which is approximated by a free wave function. So this is the Born approximation. And the question is, so what kind of effective potentials can we have? Getting very far. Okay, so let me write the note and write this down. There could be a delta of R if dark matter just interact locally with our nucleus. There's just a delta function. There is Sky, so this is the spin independent delta 3 of R. There is 1 over 4 pi R, and there is S target R, and sorry, just that, also pi R cubed. Okay? The big difference between the first line and the second line is that the first line assumes point-like interactions, So we have a dark matter that interacts with a point-like interaction. This would be the corresponding final diagram. And what does this correspond to? Well, if this is point-like interaction, what is that? What is the Sorry?
It's a long range.
That's right. This you should know very well. This is just a long-range photon, right? So this would correspond to some long-range interaction. And you remember at the very, very beginning I told you that one additional way to start to think about classifying all models of dark matter and how we want to think about it is precisely the way the dark matter is mediated through its interaction to us. And this is an example for the direct detection. All we're going to have here, this is the propagator of whatever mediates the interaction, and it's going to have something like q squared minus m phi squared. And the limit that the phi is much larger than the momentum transfer. The momentum transfer, I remind you, is of order kV or so. So when m phi is much larger than kV, right, what we're going to have is the amplitude is 1 over m phi squared. Okay, this is small. I said what? I said the momentum transfer is much larger or smaller? Well, when the mass is much larger than the momentum, we're going to have 1 over m phi squared, and therefore it's going to look like that. Right? It's a point-like interaction. This just gives us a contribution of 1 over m squared. Whereas when m phi is much smaller, when the mediator is much lighter than the relevant momentum transfer, which is the kV, then we're going to have 1 over q squared. And if you take this 1 over q squared squared, 1 over q to the fourth, write this potential, write it here and ask what is the V effective that will give you that, well, that's just that. Okay? So these two require a light mediator, these two require heavy mediator that mediate the interaction. Okay? And this is why it's so nice to work in the effective non-relativistic theory rather than the effective relativistic theory. And the reason is that there are many, many operators that can generate each of those, but because we are dealing with non-relativistic physics, we are only sensitive to these operators. So all of the information is encapsulated in this. And this is the spin independent. Let me write for you the spin dependent. Overall. So this is, we're going to have and we have S I S N over R and S N R over R. Okay, so now you can do the following exercise, and you can, which is a simple exercise. You can ask, what is the UV theory, namely what kind of operators that allow an interaction between the dark matter and the visible sector, who generate this kind of effective non-relativistic potential. It's again, with this definition, I give you the operator, you calculate that, then you can extract the V effective and so on. It's a simple exercise, so let me show you, for instance. So, how do we get delta of R? Any idea?
4
That's right. That will give you this kind of a potential. But notice, I'm writing here 1 over lambda squared. I'm writing an effective Lagrangian with some lambda in the units that I showed you before. I guess for this interaction, if this is G, this is chi, this is phi, then my lambda is m phi over G1 and G2 over the square root of G1 and G2. So there's some effective coupling, and I've assumed that M phi is much larger than the corresponding momentum transfer. Otherwise, I would have written this effective action. So this effective operator depends on makes the intrinsic assumption that I integrated out this phi, but I can only do that if the momentum, the relevant momentum transfer here is much smaller. Okay, so that's an assumption. And if it's not, then we're going to get this operator. So what about this? So that operator can be obtained from the theory of the following. So this is harder to guess. So the electric dipole moment. This is an operator between the dark matter and some additional photon, not our photon, some hidden photon. When we talk about theories, I will tell you a little bit about these kind of theories. And this is a so-called dipole, electric dipole. So it's an example of an operator that can generate that. It can also be that. We can also generate it in gamma 5 and 3 watt. Okay, since we're running out of time, let me move on. But we can literally, for each one of these operators, map all of the UV operators, all of the couplings between dark matter and us, or dark matter and the mediator that interacts with us. So this hidden photon, this F mu prime, F mu you know what it is, right? Okay, good. So this hidden photon would interact with us. So this is an electric dipole or a coupling of dark matter to some hidden photons that then interact with us. And this is the hidden photon here. So for every type of operator, we can come up with all the UV interactions that generate the corresponding potential. Any questions? Okay. So the R dependence, we said that there's some R dependence here. This R dependence really tells us about the density of nucleons inside my nucleus, right? I mean, this is the effective potential as dark matter moves through the nucleus. And as we said, as long as the de Broglie wavelength, the physical size of the dark matter, the effective physical size of my dark matter, is larger than the nucleon, this can be completely neglected, larger than the nucleus. In a moment, we'll talk about how this effect is taken into account through a form factor. Okay, so there's some form factor that encodes the information that if I increase the momentum of my dark matter, the momentum transfer of my dark matter, then the de Broglie wavelength, which goes like 1 over q, goes down. Therefore, the size of my dark matter is smaller than the nucleus, and as it propagates, it will fill all these small nucleons that are inside, and this will suppress the effective interaction, and this is encoded through the form factor. So we'll do that in a second. But for now, so let's write down for the spin-independent case the most general form of the cross-section that takes into account our ignorance about the effective potential and the momentum transfer and so on. So here's the parameterization that people usually use. So this part you already understand. Times, sorry, n minus c squared divided by b squared, n squared, sorry, times some nuclear form factor that depends on the momentum transfer, this is precisely that, times some dark matter form factor that encodes the velocity dependence and momentum dependence that arises from this non-trivial effective potential. So if we take the simplest effective potential, this form factor is just 1, We don't need to think, there's no momentum dependence and there's no velocity dependence. This will just be one, and what we'll have is this form factor that does the following. This is the nuclear form factor that we said. This is the fact that we have a coupling of dark matter to protons, and possibly a different coupling of dark matter to neutrons, and we interact, there's an enhancement that is due to the fact that we can sum up the coherence, we can sum up all of these nucleons. Okay? So people often take, again, when we look at results from direct detection experiments, people take Fp equals Fn, okay? And then the sigma dr, dE, is proportional to pi squared. So there's a big enhancement in the cross section for spin independence. Okay? With the current anomalies that we'll discuss briefly probably next time, then one way of ameliorating them we'll see, or we'll mention, is to assume a model where dark matter doesn't interact in the same strength with protons and neutrons. Since different experiments have different dependence on this coupling Fp and Fn because they have different type of materials, so Z and A are different, we can tune the coupling such that this is minimized for an experiment that doesn't see something, but it is non-trivial and large for the different experiment that sees an effect, and therefore we can ameliorate the null results with the positive results. So that's a game people play. It's actually not hard to come up with models where these are called isospin violating models, because it violates isospin. And it's not hard to come up with models like that. But anyway. Questions? Okay, so.
Those models are really fine-tuned.
Sorry, ask again?
Those models of the spin violating that are really fine-tuned to
it's not fine-tuned.
ameliorate.
You have to be careful when you say fine-tuned. What do you mean by that? I mean, it's not fine-tuned in the sense that it is quantum mechanically stable. There's no problem of writing the model like that. If we write it, it will remain through quantum operation and then
think about
you don't mean fine-tuned, but I am tuning it to have the value that agrees with experiments.
Yeah.
So it's not fine-tuned, but it is, well, it's tuned in a somewhat legitimate way, but it doesn't mean yeah. Well, I would say differently, if this was the answer, the experiments point us to the right answer. Namely, Fp and Fn are different. As I said before, I don't believe these anomalies, so I don't find this solution very attractive, but that's a matter of taste. From the experimental point of view, there is some way of ameliorating some of these anomalies through another spin violating interaction. Not all of them, just some. Okay, so finally, just is the coherence effect, the form factor. So again, we said that this should suppress our interactions once dark matter, the Broglie wavelength of dark matter is smaller than the nucleus size. So this is encoded here. This is this R dependence, and the way to do that is just to have some. So it's very similar. Anyway, it's just if you want the Fourier transform, the one approximation for the density of nucleons inside my nucleus, and this is what we call the form factor. Okay, so that's the dependence on the density of states inside the nucleus. When and I don't want to go into details now, but bottom line, we want to show that f of fn of q. So you can do this exercise and you can model your nucleus and you can ask what does this form factor look like, and it turns out that it looks like a q squared over 3 some q naught squared. Okay, so it's an exponential form where q naught is the typical scale in the nucleus, which depends on the radius. So q naught is just the 1 over the radius of the nucleus, which goes like the size, number of nucleons to the 1/3 times the frame scale. Okay? So there's some typical scale related to the size of the nucleus, and when the momentum transfer becomes larger than that, then the cross section is suppressed. Okay? Question? So I went through this very quickly. I apologize. Okay, and last comment about this form factor. Damn, I already. We had this form factor, this dark matter form factor that depends on Q and V. So again, this depends on the effective potential. So for instance, if the coupling is something like this, we get that the form factor is proportional to Q squared. If the coupling of the spin to the velocity, then this is proportional to V squared, and so on and so forth. So depending on which effective coupling we're looking at, after we fully transform the effective potential that we discussed, then we get a different type of dependence on Q and V on these form factors. So again, if we want to do something very general and we don't want to talk about the UV theory, we just want to ask, what do we learn from the results? What people do is to take this parameterization that we wrote down for the sigma dE. We have several games. F can be proportional to 1, or Q squared, or V squared, or Q squared times V squared, and so on. And we have 3 parameters, which is Fp over Fn, and the mass, of course. People fit and try to find what is the region of parameter space, which form factors, which parameterization allows for a global fit of all the experiments. And that kind of tells you, before you want to think about the theory, which theories you should be thinking about. So it's an effective way of trying to find which is the right direction, given the results. Okay? So every time there's a new result, we see these papers, and they're good, they're important if we believe the result, because that will tell you how to think about which models you want to be writing down. Okay. So what does the overall rate look like? So, well, maybe I should write down the well, okay, you saw it now. So, it's just an exponential form. We saw that it's proportional to eta, eta is an exponent, but now it's also proportional to the sigma dE, also to sigma naught, and this is and there's another suppression due to this e to the minus q squared. So this is due to eta and the form factor. Which is a function. Okay? So exercise. Show that the spectrum for inelastic scattering show that this is the spectrum, there's this exponential form, but the rate falls also as we go down to smaller equal energies. So in principle, if we saw dark matter, if we saw all these interactions, we could distinguish between elastic scattering and inelastic scattering. Okay? Okay, so one last thing before we start. So we'll go over the experiments relatively quickly tomorrow.
Monday.
Okay, so what the results from the ray detection experiments look like? So on the y-axis we have the cross-section with the nucleon, not nucleus, so they average it, they divide it by a squared. And this is the mass of dark matter, and there are two parameters. And the result would be something like that. This is a 5 GeV. This is usually 50 GeV. So let's explain the features of the problem. Why is that?
It's too long.
If it's too light, what happens?
Well, there's not much.
Right. So this is below. This is the threshold of the experiment. How low they can go depends on how little recoil energy or momentum transfer they can read, and they are sensitive to, and this therefore it goes up very quickly for a given experiment because of the threshold of the experiment. If the dark matter goes down, Q, which is proportional to, which is roughly n times V, goes down, and therefore we don't see any increase for a given experiment. Why is that? Where is this number roughly coming from? Well, we saw that the rate is roughly, that this scattering is more sensitive to the case where dark matter is roughly of order the mass of the nucleus. And therefore, this is roughly the mass. Direct detection experiments as they are right now are more sensitive to WIMPs of the mass, of the same mass as our atoms, namely of order 100 GeV. So it's not just the fine tuning, these experiments are kind of tuned to look for WIMPs with the same mass. What is this? What is this? Where is this rise coming from? Sorry?
This is the dark matter doesn't move fast enough.
That's right. I mean, we saw that the ER is proportional to rho sum over n chi. Namely, the number density. It's a dark matter mass increases. That's what you said, right? Or maybe you didn't know. Whatever. You get the point. If the dark matter mass increases, the number density drops. So the cross section, now the expected rate drops as 1 over n, and therefore the sensitivity goes down like 1 over n, namely this bound goes up like n. Okay? So the one side we are limited by our threshold, by experiment. On the other side we are limited by the fact that there are many dark matter particles because they are so heavy. And that's what the result. You will always see these regions here that are these anomalies. You will see these blobs here that are these theories that people write down such that they are not yet excluded. So this is the general picture, and we'll talk about some of the experiments.